Oh. Oh, thank you very much. I feel really small down here. So many people in such a raked room. Got an interesting question. Is it difficult to write high-performance software? What do people feel? Yes? No? How many for yes? Yeah, I used to feel that way a lot too. So I'll freely admit that. I think we've got some interesting issues in our industry. I'm going to lay out a challenge here. I think this is the main problem. Resume-driven development, CV-driven development. We keep playing with so much technology, and actually a lot of what makes code very fast is just to make it simple. So I spend a lot of my time making systems go fast. But do I spend a lot of time really thinking about it? To be honest, no. It's only if you're trying to be the fastest that's possibly out there. If you want something just to be reasonable and really quite quick, you don't have to put that much effort in. You just got to have some basic practices. So I want to talk a little bit about what are those basic practices, what should we be doing, what should we be thinking of. So we're going to talk about how we actually design for performance. What will we cover? 4 things. Let's start off with a little bit of what is performance, what's it all about. I want to talk a bit about modeling because this is actually key to it. What does it mean to be clean and representative? How would we go about building our models? And then I'll wrap up a little bit with, well, how do we actually approach testing? Testing is a kind of useful thing that tells us whether we're doing it right or not. So what is performance? What is this all about? Well, let's look at a few terms. One of them that's important is throughput. It's how many things can we get through in a unit of time. We'll also hear about bandwidth, but bandwidth is generally maximum throughput. And we're looking at, do we shift loads of stuff? A container ship is a great example of high throughput. Well, people say I'm the latency guy. Well, what's latency about? It's about response time. It's making sure we're not waiting too long so things happen quickly. So our plane can deliver stuff a lot faster than a container ship in time, but maybe can't deliver as much. So they're two quite different things. When people talk about things being fast, that's quite different. It's kind of nebulous. We need to break it down to either what is the response time or what is the throughput. We also need to care about scalability at times. And this is different. It's something that sits along the side of performance, but it's not truly about performance itself. But there's some great lessons in it. So ants are a really good example. Actually, the problem is that we're these smart apes with big brains. We actually hurt things and slow things down because we overthink stuff. Ants don't think that much about stuff. So one of the jobs that an ant has to do, which most of them do in the colony, is they go out, they find leaves, and they bring it back, and that becomes food. Now, their little tiny brains have got some problems. So, for example, whenever they go to get a leaf, quite often they'll grab the leaf with one set of pincers and the other one starts to cut. 50% of the time, they cut the wrong side and it falls on the ground. And then they start all over again. Now, you could look at how could we optimize to do that better and give them a much larger brain, but actually that's not where the problem is. The problem is getting the leaf back to the colony. That's the hard part. That's the long, difficult part. And this becomes actually quite a common problem in performance is we will optimize for the local things and miss the big picture. So if we're going to spend effort, we need to spend effort in the right sort of places. And very often how we set up our teams is we'll focus on the wrong areas. So a lot of my life is doing this sort of thing. I'm waiting at border control. And as I'm sitting waiting at border control, I get to think a lot about clients I'm going to see, stuff I'm working on. And I just realized, having done this quite a few times in the last few years, this has got everything you need to care about in performance. It's got queuing theory. It's got parallelism. It's got concurrency issues. It's got work stealing. It's all sorts of the really important things that are out there. And actually, most of it's not that complicated. So let's look into this in a little bit of detail. One of the bits of theories we need to care about is queuing theory. A great piece of work that started here in Stockholm 100 years ago with the work of Erlang. Or actually, not Stockholm, Copenhagen. Got that one wrong. Mixed these two up. So Erlang was realizing that sometimes you go to connect in a telephone exchange, you end up waiting for a long time. And what he realized fundamentally was happening was probability theory was coming into effect. So if something's being utilized, you end up having to wait to get to use it. So you turn up to use something, somebody's already using it, you wait, you take your turn. The more it's being utilized, the more you're likely to wait. And everything's kind of great until 50-60% utilization, then things start to go bad. And once you pass about 80% utilization, response time gets really poor at that point. So if we want our systems to be responsive, we've got to keep utilization down. That applies to everything. If there's any project managers in the room here, here's a shout out to you. Humans are a system as well. If you run your teams at over 80% utilization, they will not be responsive. It's the same set of problems. It's math. You cannot beat math. So ensure you've got sufficient capacity, and then you'll be able to respond quite quickly. Well, can we go parallel? We've seen all of those lines. So if we do things in parallel, we can get more work done. But there's a fundamental problem with that. Many people may have heard of Amdahl's law. And what Amdahl was making a point about is, if you break something up to go parallel, there's always some part of an algorithm that is sequential. And for that part of the algorithm that's sequential, it becomes a constraint on the speed up. So if part A of your process can be done in parallel and you've got 4 CPUs, you can get a reasonable speed up. If part B is the only bit you can make parallel, you can get much less of a speed up. So the amount of the algorithm that is sequential will dictate the ultimate speed up you can get. What's this look like when you graph it? So if half of something to be being parallel, you can never get greater than a 2x speed up, because you can infinitely cut down 50% of it to the point where it becomes insignificant, but the other 50% still has to be done in a sequential fashion. You cannot get that speed up. So that was a really good argument to say why we need to be careful about going parallel. It's not the panacea. But it actually gets worse than that. So the work of Neil Gunther, scary formula, it's actually not that scary when you look at it. He realized that in the field, the contention penalty was part of the problem, but actually coherence can affect it as well and become an even bigger factor. So we need to figure in coherence to the problem. Now, what do I mean by coherence? When multiple parties are working on the same algorithm and they need to share data, that data needs to become coherent with the different parties. I've seen a lot of Hadoop jobs in the wild where people say, I'll throw more machines at it, it'll get faster. We end up with this sort of scenario. So the blue line is Amdahl's law. In effect, we're seeing the speed up. But let's say for that work that's happening, we throw in 150 microsecond penalty to make that data coherent across machines. After a while, that starts to dominate. 150 microseconds in a data center is not a lot. You put these sort of things on Amazon, that becomes a common problem. So you throw more machines at it. Does it speed up? It actually starts to slow down after a while because the coherence penalty starts to dominate. So we've got to think about these things. You just can't run away from them. Anyone know what that graph is likely to be? Now, what's on the axis? Over here, we've got time, and that is in nanoseconds to complete a job. On this axis, I've got numbers of threads. And as I increase the number of threads, this is going up. Something's taking longer to happen with the number of threads that's going on. The fact that it's a completely straight line, if I look at this from Amdahl's law or universal scalability law perspective, this algorithm is 100% sequential. You cannot get any parallelization as you speed up. What would cause something like that? Logging. Our loggers are a perfect example of how to hit Amdahl's face, or have Amdahl hit you right in the face and slow you down. So if anybody is using loggers, please don't use the synchronous loggers. At least go asynchronous and get that to start becoming a curve at least. But so many people go synchronous. The design of our loggers is a complete nightmare and a real problem. I've seen people put a load of effort into their systems to perform really well, and then they put a logger in the middle of it. And it just constrains everything for throughput. So we have to watch out. There are other solutions to this. So that's a little bit of the theory. Let's look at what should we be doing for our models. I'm going to start off a little bit with what I mean by clean and representative. So let's go back to the dictionary. What does clean mean? Because we hear about writing clean code. That sounds like a nice thing. According to the dictionary, it means morally uncontaminated, pure and innocent. Most code I see doesn't meet that definition. It's very contaminated in many ways, mostly with all sorts of horrible frameworks and stuff that we put in there within Poe's ways of working. Representative is serving as a portrayal of something, being an accurate representation. I love to think of code as the place where I capture my understanding. Yet, you read so much code and you see variable names and class names, and they don't make any sense in relating to reality. They're all sorts of weird things. It should be a good capture of what's going on. So this is the place where I like to capture my model. And what do I mean by this is, like, if I'm working on a problem and I capture my understanding today, my understanding is going to be imperfect. That's fine. That's human. Tomorrow I learn something else. I should update the model. It's a reflection of what I currently know. Like, how many people have worked on a system where it's coded up one way, and then a year later, everybody knows so much more about what the real solution to the problem is, but you haven't changed the code? And you spend the whole time bitching about it. We got to update these. These are the things that make it better. This is what makes it work. And this has to be for the full stack on what we're dealing with. Abstractions is another good thing. So again, this is one of the interesting problems of having lots of smart apes working on a project. My rules of abstraction. First rule, don't do abstraction. Second rule, don't do abstraction. Well, actually, I'm being a bit sort of joking about this. Yes, abstraction can be a useful thing, but let's wait until we see at least 3 things that genuinely are that thing that's going to be abstracted. The smart ape problem is we run to abstraction before we even truly understand the problem. It's much better to not be constrained by an abstraction. So you look at a problem and go, oh, I think that's one of those big baroque crazy things, and you create that and you leave this legacy. And then you try to fit the second and the third thing to it, and it doesn't fit. And because you kind of give birth to this monster, you keep it alive. Start it off the other way around. Code it up just to be what it needs to be. You find another one that's kind of similar. Don't be constrained. Code it up again. Maybe you do it the third time. Now you've got a couple of really good examples to see where are the abstractions, where is the true commonality, then extract the abstraction. Don't go at it the other way around. And abstractions have a cost, so make sure you're using them and they're paying for themselves. How do you know something's going to pay for itself if you put it in up front? That's a kind of crazy thing. What to watch out for? It's dry. We have the mantra of dry, don't repeat yourself, so people will start abstracting far too early. That leads to coupling. Everything has consequences. Yes, code duplication everywhere is a bad thing, but coupling everywhere is also a bad thing. What is the lesser of the evils? We need to work that out for the problem that we're actually dealing with. So if we go to implement abstraction, and yes, there's abstraction in the mathematical sense, there's abstraction in many other senses, but let's take OO as an abstraction. So we want to create a type. Well, if we create a type, we have to end up dealing with polymorphism. And the way polymorphism works is you kind of got a number of ways that it'll play out. If you only have one of something, you end up with it being monomorphic. Our runtimes can make that quite efficient. If you've got 2 of something, it's bimorphic. There's some choices that you can make. It can still be reasonably efficient, but it has to do a bit of branching. If you've got more than 3 or more something, it becomes megamorphic. This involves jump tables, indirection, all sorts of things to pay. You have to pay to get those benefits. So if you're getting those benefits, are the costs paying for what you're getting in return? We need to be able to answer those sorts of questions. And we'll talk a little bit about branching later on processors. And fundamentally, it has to be representative, or you've got a big smell in your model. The code should be easy to follow, easy to understand. I'll show you some examples of how we'll take this right down the stack, and the simpler we make it, the faster it will be. It'll also be easier for people to deal with. So what I like to kind of come in is thinking and say no to big frameworks. I don't know what's happened in Java. I'm an old C programmer, and I came to Java, and the first thing that really shocked me was I seen libraries do their own logging, and they imposed logging frameworks. It was like, that was a WTF moment. Why are you not returning error codes? Why are you not having callback handlers so that I can have the choice? And I think this is the big problem of our industries. We impose ways of working on other people, especially in the Java community, rather than giving the choice. If you've ever backpacked around the world at any stage, you'll find one of these two types of people. You find the people who know how to travel light and know what is important and they don't carry any unnecessary stuff, and you'll find the people who bring everything. Try find the people who like to travel light and put those on your projects. You'll have code that's much easier to maintain, much easier to deal with, and it'll tend to be much faster as well. That's the kind of resume-driven development approach, I think, that drives a lot of this other behavior. So what does this mean for abstraction? It's like, just a reminder, do it whenever we know the benefits and we're sure we're going to get that return. Anyone heard of Joel Spolsky's law of leaky abstractions? Probably lots of this. And what's kind of interesting is he points out that a lot of this is because the complexity of the underlying, well, it's actually because we're getting abstraction wrong. It's become so commonly misused, we have a law of leaky abstractions. Let's go back to Dijkstra. And whenever he had his Turing Award speech, he made this statement in the middle of it. And I think this is really what abstraction should be about. The purpose of abstracting is not to be vague, but to create a new semantic level in which we can be absolutely precise. How often do we see abstractions that make it vague that's underneath? That's where it's the wrong way around. We've got to be thinking that sort of way. So let's take an example. Our memory subsystems, whenever we're dealing with main memory, who believes that all accesses to main memory are equal? We're told it's random access memory. It should be giving us equal style performance. So let's say I was to walk through memory completely linearly, and what would be the average cost of a memory access? Anyone have any idea? How many nanoseconds is an average cost? Yeah, so that's a good point. It depends on the memory. So I'm going to assume DRAM on x86 on a modern Xeon server, which is pretty much what most of our code will be running on when it goes live. It's less than 1 nanosecond when it's pipelined. Less than 1 nanosecond. If I go randomly all around the heap, it's more like 100 nanoseconds. That's 2 orders of magnitude difference. So your pattern of access really matters. And our hardware friends have put a lot of things in place to make things better. We don't need to know all of those things. I could talk about translation look-aside buffers, I could talk about prefetchers, I could talk about all the different translation modes and the different things that can happen in parallel. But to abstract this, we need to know 3 things. One thing we need to know that is our hardware friends have thought of, if we're going to use something, we're likely to use it again in the near future. They've taken care of that with what they call the temporal bet. They also look at things from a spatial perspective, so things that are close together tend to be used together. So that means for our models is they need to be cohesive, and I'll touch more on being cohesive in a second. And the final bet is they've taken a bet that we will have predictable patterns of access. So we will walk memory in a predictable way, like we will walk over lists or structures in a way, and they'll prefetch that for us. If we don't respect these 3 bets, we're at the slow end of everything. And that's the level of abstraction we should be thinking about. So you don't need to know the detail, but you need to know that. And that becomes important. So given that, what does this mean if we go and model? Classic one is coupling versus cohesion. I find this whole crazy world talk now about microservices fascinating. They're cool, they'll give us decoupling. Who talks about cohesion? Has anybody been to a microservices talk where someone actually talked sensibly about cohesion? Because that's important. That's really, really important, and we're not talking about those sorts of things. The fun is in the interaction. Which bits of behavior are going to be together and going to be cohesive? So they talk about all the decoupling, but there's consequences. Everything's got consequences. There's no thing as really good and bad. There's benefits and consequences, and we have to be aware of that. What's a good example? Really, really simple example. So I build a lot of queues, and queues are handy enough from producers to consumers. We typically have buffers So for people who are familiar with Java, this won't be a surprise, but if you're from other languages, it's all kind of similar. We usually have an array that we're storing the data in that's being buffered, and what will typically happen is people don't do the likes of this. So from a modeling perspective, they will rely on buffer.length, for example. That means you're now having to interact from this object across to another object to find out its length. That is programming by side effect in how you do it. You haven't actually represented the model. It's not clean, it's not representative. And where does this become a problem? So that's not a big deal. And in fact, actually, if there's any VM people here, they will talk about how in later versions of the VM, we're now going to be able to optimize and remove bounds checking if we use some of those things. But there's also features we lose as well. So if I'm typically going from producer to consumer, one of the interesting things you see a lot with queues is queues are always either empty or full. They're very seldom in between. You burst the traffic that filled the queue and then has to be drained, or you're sitting in an idle state waiting for traffic. So you're full or you're empty. Our underlying hardware is not bits and bytes just on their own. We move data around in blocks of data. Those are known as cache lines in our cache subsystem. There's 64 bytes at a time on an x86 processor. So if I've got a queue and I've bursted a bunch of data and I've sort of gone around and caught up from producer to consumer, they're right next to each other in a memory subsystem. They're sharing the same cache line. We get an effect called false sharing. How can I very easily separate that? Well, the fact that I have taken out the concept of the capacity, I can make capacity to be the size of the buffer as a length, say minus 32. And now I can put things apart and get some quite significant performance benefits and better behavior. But all I've done is modeled correctly what I want. I'm pulling out the concepts. If anybody receives any of my code, I don't like to comment code because I think comments don't reflect really what's going on because the code changes so much, but give nice descriptive variable names, nice descriptive class names, capture your understanding. And then you've got that sort of flexibility. So you're showing what bits of information you want to be cohesive, and they should be there. If you're having to interact or work out something by side effect, it's much harder to understand. It also becomes much harder to optimize. Many classes I see, they become a properties bag. They're just a bunch of stuff put together, and it's not cohesive. And you get things like feature envy. So class A has got access to a class B, and it's constantly asking for values from the other class. So we call that thing feature envy. That class is not cohesive. We move the fields to where they should be. They're now all together. They're now respecting the spatial bet that our hardware gives us. So good modeling gives us good performance. It's really simple stuff. So a lot of what you'll find with really high performance code is it doesn't look like a whole pile of compiler tricks and bit twiddling. It's actually just really clean, elegant code that expresses exactly what needs to be done. So just keep things really, really simple and keep things cohesive. One example I have on this is I go to learn a new code base. I usually work my way around the whole model. And as I work my way around the model, I refactor it for things like where I see code smells, where I see feature envy, where I see things that should be normalized better. And just by doing that, I usually take a benchmark before and a benchmark after. And pretty much every time I've done this, there's about a 30 to 40% performance improvement just by cleaning up the model. And it's a lot easier to work with afterwards. How do you know what things should be put together? Actually, a really good rule of thumb is you usually see change happens in clusters. And that's usually a really good indication of what should be together. Things that are cohesive tend to change together, and things that are separate won't have change happening to them. So it's good modeling, good things to do. So we have to respect this locality of reference. So as we get into this world of microservices, if you're bad at modeling, if you don't get cohesive design, you're going to make in so many remote calls, your performance is going to suck even more than it is in a monolith. So these are the sort of things we've got to start thinking about. We've got to keep the communication down, we've got to keep things well decoupled, and keep the things cohesive that should be together. Relationships. So we draw all these little boxes, and we draw lines between them. So if we're doing a modeling world, so I do a lot of work in finance, and we tend to have order books, and we have orders that sit on those order books, and people will just draw a line. The really interesting thing is, what is the detail in that line? If we look at it, it's actually two relationships. We've got bids and offers. It's one to many. We dig into it a bit more. It's also qualified on price. And it tends to be ordered in a FIFO manner. So start thinking about the detail of the relationship. When we drill into it, like, I'm not even talking anything about computer science here. I'm talking about truly understanding the business problem and reflecting it. Once you've done that, you can pick the right data structure to represent that relationship. And that becomes really important to the performance. Like, if you just randomly choose a data structure to address that, you're not going to get the right performance because you're not going to be walking the relationship how it's intended to be used. And when you talk about like learning all these great frameworks and doing resume-driven development, I give one piece of advice, and I think I've seen this hold true for decades now. If you learn data structures, they'll be useful to you for your entire career. Like, lots of the stuff that I see people rediscovering, Donald Knuth wrote it down in his books decades ago, and it isn't changing. This is all really great stuff. So make friends with your data structures. If you want to spend time studying, study data structures. They're useful, and they'll stay with you. Also, when you start thinking about your design, jumping to code's a good thing, but it uses one set of pathways in your brain. The more sets of pathways you use, the better your understanding, the clearer the view you have of your model. So try documenting it, try write down your understanding. Like, that can be as simple as a wiki page. Put something like that together. Discuss it with your other team members. This is one of the benefits of pair programming. Don't just sit together and one person looks on to the other. Have a discussion. You'll use different parts of your brain. You'll understand the problem much better by doing that. And by doing this more upfront, by the time you get to code, you'll find that code becomes much more of a typing exercise and with a nice feedback cycle. But do take the time, go think about it. Algorithms. So we talk data structures. What are the algorithms we use? Well, many people will look at sort of the order of algorithms. We'll talk about big O notation and all these sorts of things. Well, that's a useful thing to know, but much more interesting is if you actually measure. Because we'll all make mistakes. What I like to do quite often is write my system, then measure it and see, do I get the orders I'm expecting? Because quite often, n may be small, constants may become really significant. So what is the realistic performance? And the really important question all the time is asked, what is the magnitude of n? I've seen people put in complicated data structures and you say, well, how many of those things are there? Well, about 50. Just stick it in an array then. Make it simple. So know the magnitude of n and know whether n's likely to grow or not. If you're not sure it's going to grow, well, you want to protect against that. If you think it's not going to grow, make your life easy. Really good database people obsess about the cardinality of relationships, and it's a great thing. It really helps them understand the model, and they do well. The other major point is our algorithms. Those are the key to your service time. So if you go back and study queuing theory, you will study that the fact that service time is key to what you do. And if it's non-deterministic, it makes a lot of your models more difficult. Your algorithms is the one thing you can generally control. You can't control arrival rates often to a system. In fact, you don't want to. You want as many customers to come whenever they are able to. You just want to offer good service when you can. Batching. I often hear people say we have to trade off latency versus throughput. There are a few cases where that's true, but generally it's not. And batching is a great way we can get rid of a lot of the expensive costs in our system. We have to go to network, we have to go to disk, we have to do all sorts of interesting things. So here's the kind of classic example. Multiple producers are going to write to a storage device. I'm going to pick on logging again, because this is pretty much how it happens. So our producers are going to produce log entries. If they're going to write down to storage, they all have to take a turn. And that means that if they go to do it at the same time, one of them's first in the queue, one of them's going to come behind, and then another one behind that. So the one that's at the back has to wait for everybody else in front and slows it down. Amdahl's law comes into effect. How do we make that better? Well, if you go to something like async appender, there's usually some sort of structured buffer in between where you can write into that with a much shorter space of time. Then you have a batching thread the other side that can take huge chunks of that out and write it down to disk as soon as possible. If this is actually done really well, you'll even do it out of process and you won't lose anything. So people say, well, I'll use a synchronous appender because then I won't lose anything. They write to a buffer and then they return. And they wait on another thread to eventually fill that buffer and write it to disk. So usually whenever a system crashes, you generally have lost on average half of your buffer, which has the interesting data in that probably would help you debug it. So I just think logging systems for me is a fascinating case study on how to do everything wrong. If you batch well, you go to that blue line rather than the red line from a queuing theory perspective, because you start reducing the utilization on the resource. You use it really, really efficiently. Eventually, everything saturates, and you end up going up the curve a bit. But the world is good for much, much longer, and so you deal with your underlying resources much better. So, tip for this is study batching. It's a really useful technique, and you can apply it in lots of places when you start looking out for it. Branches, branches, branches. I mentioned this before, I'll come back to it. What do I mean? Well, in our code, every time we have an if statement, a for statement, a while statement, a case statement, these all are branches. Our modern processors can try to go ahead in your code and try to make as much progress as possible. They're really fast, they can do lots of stuff in parallel, but quite often they'll reach branches and they don't know where they're going to go. They'll predict the branches, and in fact, these days they predict branches really, really well. But if the branches aren't there, they can make even greater progress. I see code like this a lot, where you've written something, you want to do some stuff to a list, you get the stuff like, okay, let's check if it's null. Or even better, I'll optimize the code for the empty case, when an empty case is really, really infrequent. So you penalize the common case where you've actually got real work to do. Like, come on, this is 2016. Do we really still need to be using nulls in our code? We gotta get over this. I got to meet Tony Hoare last year, which was a real privilege for me, where he came up with the null pointer and he calls it his $1 billion a year mistake. Yet it still continues on. Just get rid of code like that and make sure you're always dealing with a genuine collection. And if you have an empty set, you just deal with it exactly the same way. This will make your code simpler, make it faster, get rid of a lot of branches. Just make things elegant. Don't keep trying to think of the optimizations that aren't actually relevant. We shouldn't be doing stuff like that. And we should be respecting the principle of least surprise. Don't have functions called and pass nulls or maybe pass a full thing. Always code up to be passing a genuine object. That's the way we should be thinking. It'll make it a lot cleaner and much easier to deal with. Loops are an interesting thing. I've seen all sorts of statistics that basically 80% of the entire time in our code is spent inside loops. So loops, from a performance perspective, is really where we want to spend our time. I love this quote from Blaise Pascal. Many people attribute it to Mark Twain, but I think Blaise Pascal brought it up much earlier. But it's basically, if I had more time, I'd have written a shorter letter. This applies so much to code. We tend to write code, we rush on and we pick up the next feature, especially core code in our system. I think you should go back and read it regularly. It's one thing I like to do is keep going back, rereading old code. It has a number of really interesting effects. Is you see things that you didn't see the last time. Like a classic one, you'll even see this with normal written prose. So you write an email today, you read it back to proofread it and you send it, you don't see the mistakes because your brain fills in what it thinks you wrote rather than what you actually wrote. You go read it tomorrow, your cache is empty, you've forgotten what you thought you wrote and you read what you really wrote. And then you realize, oh yeah, it's full of mistakes, I need to fix those. It's exactly the same with code. Write your code, leave it, go away, come back, and you go, yeah, I could write that much better. Like code that you write now, and then you read in 3, 6, whatever months' time, it's code written by a different person. You're writing it for yourself. Go back, read it regularly, you can do much better. Now, why does this really matter for loops? Well, in our modern processors, we take instructions, we have to decode them, so we turn things like macro operations into micro operations, and so that's a decoding process. It uses a lot of energy in our processors. Then on the back of that, we have a micro-op cache. there's just over 1,500 instructions that fit in our micro-op cache. If your loops fit inside there, they tend to go really fast, really predictably, and don't produce as much energy, or don't require as much energy in our processors. And so if you fit inside those loops, you get better performance and all those other things. How do you know if your code fits inside that? Well, we have CPU performance counters that tell us that. You can see whether you're churning some of these caches. So it's a useful thing to know. There's also another cache ahead of that, which is much smaller. And that is the micro-op queue going in to be actually executed. And it'll be between 28 and 56 items, depending on what processor model that you're dealing with. Now, what's our takeaway from this? That little queue in front works really well on very small, elegant pieces of code. Code that has no more than 8 branches in it, has no other function calls and no returns in the middle of that. It can blast through that really quickly. The outer loop can deal with more complex code. So what does this mean when you write code? Follow single responsibility, and it works really well. So if you've got a loop and you're running over some data and you're doing one clear task, that's easy to understand. It's easy to test. It's easy to debug. You need to add another piece of logic in. If you add it into that loop and now your loop has got conflated concerns, it's doing multiple things, you'll be surprised how often you will hurt performance rather than help. People make the assumption that, well, if I was to go over it again, that would be slower. More often than not, it's faster to go over the data again and do it that. And that's nice and clean, nice and easy to test. Now, that doesn't always hold, so you have to measure and find out. But one thing's for certain, don't jump to the assumption that if you add the extra code into the loop, you will make stuff faster. You're more than likely going to make it slower. So keep your code simple. Follow very clean patterns of just doing one thing per unit of whatever. I like to think of like the core loops in your program, craft them like pros. Go back, reread them, deal with them again. They'll also be much easier to maintain and they'll reflect your current understanding. Composition is another interesting thing. For this, size really matters. This is a great quote from Cliff Click, who wrote one of the JIT compilers for the Hotspot VM. In a discussion I had with him once, he just says, like, the one point to take away is inlining is the optimization. Because once you've inline code, you can do so much other things. So people will, if you come from a C background or some other languages, you think, I'm not going to call all these functions, because if I call these functions, that's a function call overhead. I'll just make a big, huge method and put it all in it. You're much better off having nice single responsibility methods and let the runtime compose them together and inline them. It will inline them based upon the real data usage, not what you think it is in advance. Another really good example of a client who I was working with them on this, and they had very large, very complicated methods, and we broke them all down into nice small, clean methods. It was easier to test, easier to reason about, and the system in some parts was 4 times faster as a result. Simple, simple, clean stuff. Just make it easy to deal with. Keep saying this again, single responsibility. I've got a mantra is one class, one thing, one method, one thing, one statement, one thing. It works, it fits in my small brain. But it really works from a performance perspective as well. And from all of these small atoms, you can compose anything that's big and complicated, but keep it small. APIs. I'll pick on something from Java for a second. There's lots of good examples in some of our older libraries. I spend a lot of time working with networking code. And so if I want to find out if a socket has got data and I've got lots of sockets, I end up creating a selector using NIO. So you're probably all trying to take this in, and my sort of eyes are bleeding generally when I'm reading code like this. It's not easy to follow, but it's also got some horrendous performance issues. Like things like this. So every time I go to pull the sockets, I have to get a collection of the selected keys. This causes allocation. If you trace into this code, the amount of locks and complexity in there is really, really high. And then we create iterators, we go over the iterators, and maybe eventually we do some real work. And if you end up working a lot in this area, I know people who have worked on lots of different I/O frameworks, you end up doing horrible things to get around this. Like I've had to use reflection, go in and change some of the structures inside to replace them with things that are more sane. that don't create so much garbage and just grind performance down to being unusable. But this is because of the API design. It's like not giving the caller choice. And I think this is it's kind of Conway's law in action. Maybe it says something about the mindset of some people who design these sorts of things is you need to think and have a bit of empathy for your customer and give them the choice. Now, what would giving them the choice look like? So let's say I had an API design that looked more like that, where I could allocate my own collection in advance and I could reuse it if I want to, and then I just say select now and I pass in the collection that it will go and populate. That's a lot less code, and then I can iterate over it. Well, people say, well, okay, that's kind of functional. It's a bit like Java 8. Yes, it is. But we could have done this back in Java 1 from a design perspective. It's just changing the API designs. There's loads of other good examples of this. If you ever look at something like string split, it's horrible. I blogged on this and thought about giving the caller choice. The amount of flaming I got as well was hilarious because people were saying, you're writing code in a C style. You should be returning things like that. Yes, the core libraries are returning stuff all the time. I think it's wrong. It's wrong from a performance perspective. It's wrong from a caller choice perspective. Because like, if you take the string split example, you get a return with being an array of tokens. You then have to do something with that. So if I want a distinct list, I'd have to put it into another collection and then have to do something else to it. Why can I not provide the collection for exactly what I want to do? Give me the choice. So start thinking about how you design this. Data is another great thing. We're often just dealing with great big grids of data. And we've got this disease of turning everything into DTOs. And DTOs have got lots of indirection, they've got lots of extra baggage that come with them. Well, what else can you do if you want to deal with a big table of data? How about creating a number of arrays, where each of the array represents what would be one field in an object. So that's a customer, might be forename, surname, date of birth, whatever it was. We create them as separate arrays. How do I identify a particular object? Well, it's just the row. If I want to scan down by something, I can do that. I can scan down all the dates of birth. I can scan down all the forenames. It's nice from a memory locality perspective. It's respecting the bets that our hardware friends have done. I can just walk down through these. Sometimes data is just data. And let's treat it this way. I don't know where the DTO thing came from. It just baffles me. There's a lot of great work elsewhere. I think it's really funny that the OO community and the functional community kind of fight when they can actually learn so much from each other. There's so many great things. I love to program in different paradigms, and I think you learn a lot. Like a great tip I was taught a few years ago was, how about if you're writing OO code, you write your tests as functional style? Or if you're writing functional code, you write your tests as OO. It gives you a really interesting dimension on a problem. You see things from another angle, and you spot things that you can do better. So there's a lot to be learned from looking at other techniques. Now, we've done all of these things. Do they work? Do they not work? Well, ultimately, we have to test. First thing that you must do is define some performance goals, because when are you done? If something is good enough at 100 transactions a second, you're done. You don't need to do 500 a second. If you happen to develop nice and cleanly and it turns out it can do 500 a second, great, that's just a benefit. But you're done whenever you meet your goals. And it's usually good to ask, well, what happens if I don't meet the goals? Because that's usually where the interesting trade-offs happen, where we decide what's right and what's wrong. So how do we measure response time? Who here uses average? So average number of transactions, average response time, average latency. It's really bad to do that. Why is it bad? So let's say I capture every single transaction that goes through a system and what's the response time of it. This is what a typical financial system will look like when you capture everything. We get this distribution. Now, if you use the basic statistics terms like mode, the most common case that you see, that actually tells me something reasonably useful. I can do something with that. Median, that's not very useful. It's not telling me anything interesting. Mean, that is completely useless. It's telling me nothing interesting. Like, it doesn't tell me typically what is going to happen. It doesn't tell me what all this bad stuff is out here and why that's been caused. It hides all of those things. We need to think differently. A subject I recommend you look up, I'm not going to spend much time on it, is called coordinated emission. We end up deceiving ourselves about how a system actually performs. With coordinated emission, what we start looking at is we will capture all of the response times, we'll put them in a histogram, and then plot it as a percentile distribution. So 90% happened to this level, 99, 99.99. Interestingly, whenever you plot those sorts of things, if you see lines like that, you've probably done something wrong. And that's usually because those sort of things don't happen in nature. And there's usually step changes and stuff, and there's usually missing data. Those other two lines are a corrected version of what was really going on there. So that was a customer of Gil Tenez who let us share that as just the sort of things that they were seeing. And it's fascinating what can kind of come out from this. How can you capture that? Use a tool like HDR histogram. It will cost you a few nanoseconds to record each event into it. You can record every single observation you have in your system of response times and other things. Then you can produce those graphs, and now you're not blind to what your system's doing. You can see what's going on. Whenever we go to test, we have now got some good testing tools. So things like Java Micro Benchmarking Harness is a great way of making sure we can warm up our code, get it to reach stable state before it's actually doing measurements. And it's important to reach stable state because you don't want to be measuring it before the runtime has got to produce your compiled code, before it's got to inline and optimize and do all of the right sort of things. And running these sorts of things become a very useful thing. Whenever you've got bad performance, we can use all sorts of profilers, but sometimes we can go right down to the CPU and find out what it's doing. Are we cache missing a lot? Are we having too many branches? Have we got too many other problems? Our CPUs can tell us all of this. They have counters for pretty much everything they do, and we can get access to those. They're called the MSRs, the Model Specific Registers. Tools like Linux Perf can let us get access to those. Other great tools that are open source like Liquid, it stands for Like I Know What I'm Doing. Very useful tool, really nice. And can also do like nice, pretty ASCII art pictures of how your hardware is laid out, where your network cards are connected to which processors, and all this useful stuff so you know what's going on. Cool. So wrapping up quickly, we need to, once we're doing this, we need to make this part of CI. So it needs to be part of our continuous integration so that we know all the time when it's going wrong or when it's going right. Have it so that you hard feel whenever you drop below certain performance targets, but also trend. Graph up trends of whether you're improving, degrading, whatever you're doing. Make this part of what you normally do. When I was at LMAX, we put big screens up on the wall and we graphed our performance, and we could see our trends, whether we're getting better or whether we're getting worse. And sometimes you get a big step change. We may not go below threshold, but we've got a step change because we introduced something that was a mistake. That's beforehand. Once we're live, we often don't know what's going on in our live system. So I recommend putting telemetry into your live system. Let me say that again. Put telemetry into your live systems, please. Well, what do I mean by this? You need those counters, those histograms capturing what's going on so you're not blind. Don't have your customers complain to you that it isn't working. Know before. Know how your system's actually performing. You can put counters in for all sorts of things and make them available. There's lots of good examples out there. Grab me if you want to see some examples of this for real. Same with the histograms. You can capture them, you can serialize them, you can log them, and you can see over time how everything's working. So quickly in closing, think of getting your code clean, and that means get it uncontaminated from all of those other bits of technology that don't make any sense. Make sure it's a true portrayal of what you understand, and measure, don't guess. There's a great quote from Bill Lear, who invented the Learjet, and he used to say it with aircraft design: if it looks good, it will fly good. I find it's very true with code. Code that's clean, simple, and elegant, you can pretty much guarantee that when you profile it, it'll generally perform really quite well. So aiming for the clean, get it nice. And on that, I'll wrap up. I'm not sure how much time I've left.
We're about out of time, so.
Sure.
How do you deal with the allocation rate, that you do not allocate a lot of small specialized objects? Do you like pull them or reuse them, make them mutable in order to kind of supply them with the state?
Sure. So the question is, how do you deal with allocation of objects to keep it simple and get performance? It depends on the class of problem you're dealing with. If you're dealing with extremely strong response time guarantees, like in high frequency trading, you may pool objects or you may allocate at such a low rate that you don't experience a GC event in the same day. That's at the extreme. Real world applications, our GCs are not bad. The thing that you've got to do is not allocate wastefully. So it's like anything you do, you'll pay a cost, wahee, and you may or may not get benefits for that, but you've got to measure. So like allocate, but don't allocate wastefully, I think is the answer to that. And you can see that from your design and profiling. Yes, so do accept mutable objects. I think mutability is a great thing. Like if things are very short-lived, it can tend to do well. Just don't do it unnecessarily. Like these layers of DTOs and lots of other things and stuff, that's usually where the waste is. If your core problem you're solving requires some allocation and you can use mutability to keep it nice and clean, you'll generally find that the garbage collectors and everything will keep up. Just don't put in layers and layers of stuff that's just not adding value. Okay, well thank you all very much.